As you may know, OpenFOAM has already become a significant numerical tool for both fundamental and applied research. So since we start to organize this webinar, we received many warm feedbacks and support from our colleagues. So thank you all. Today, it is our great honor to have the OpenFOAM principal developer, Professor Hrvoje Jasak, to give the first talk of this webinar series. So I think most of you already know Professor Jasak due to his significant contribution of OpenFOAM development. But please still allow me to introduce him before he starts the talk. Professor Jasak is a Guiana Anglo-Polos lecturer in the Cavendish laboratory in University of Cambridge, and a director of Wiki Limited. Professor Jasak is one of the two original co-authors of OpenFOAM and a member of OpenFOAM Governance Steering Committee and the chair of the OpenFOAM Numerics Technical Committee. His research interests are on numerical simulation methods and the mathematical modeling of continuum phenomenon and numerical modeling in multi-phase and free surface flows. Professor Jasak's active projects are in the area of multi-physics modeling of complex coupled systems, such as battery modeling and extra-scale HPC applications of linear algebra and others. So the title of this talk is Simulations of Reacting Flows with OpenFOAM. If the audience have the questions, please submit the questions through Q&A or chat function. Okay, I will help ask to Professor Jasak on your behalf. So Professor Jasak, now the podium is yours. Thank you.
Thank you very much. Welcome everybody. It is my honor to be in Singapore, only virtually this time, and I hope that will change in the future. I also would like to thank Hrvoje for inviting me to do this talk. It is a great honor to speak to so many of you. And I also need to say hello to some of my friends in the audience. It is particularly nice to be able to come together in this way. As you have heard, I've got two jobs and they are both busy and painful. So I have asked for special permission today from Professor Zhang to make this presentation as long as I want. In reality, I don't know how long the presentation is going to take. I'm hoping we'll finish in about an hour. So please save your questions and write them up, and we will have plenty of time for discussion afterwards. So I would like to talk about the simulation of reacting flows, and there are obvious things that we need to discuss within this story. The most important, of course, is why should you bother with OpenFOAM as a model implementation platform for combustion modeling? Because there are so many different ways that you can do that. There are practical requirements and there are pre-implemented models that help you with that. But what struck me is that I really need to take you to the beginning of the story. I think it's been mentioned that I did my PhD in 1990s with the group of Professor David Gozman at Imperial College. And at the time, as far as in-cylinder and engine combustion, this was by far the coolest group in the world. So I will show you where we started from and what are the current limitations and requirements that we have to work on. Of course, there are many different aspects of combustion today, not just internal combustion engines, but anything from large power plants to gas turbine combustors to burning biofuels and various other requirements. And now, towards the end of the era of an internal combustion engine, the new areas, which are really close to combustion in its nature, are really coming up again. And a lot of the machinery that we have built will be able to be transferred there. So I've been obsessed with fuel cells for about 15 years. So that's another way of consuming fuel, but you have more flexibility. And also you heard that I started working on battery modeling. And this is both microscale battery modeling for lithium-ion batteries, and also macroscale modeling for things like liquid metal batteries. And what struck me about it is that all of these problems really rely on the same basic structure that we need to provide. We are solving continuum modeling equations. We are solving for concentration, conservation of mass, momentum, energy, and various additional phenomena. So going through this story, we will come about 2/3 of the way down, which again brings us back to the beginning, okay? But I'll keep that twist for a couple of minutes and dive straight in to the story. So not many of you will recognize one of these geometries. This is actually a Daimler-Benz M111 engine from about 1990, where a lot of initial work on in-cylinder CFD has been done, okay? And here is a bunch of pictures, and you will see that there is the logo with C and D, which represents Computational Dynamics Limited. Now that code has been evolved into star CCM+. And we were actually able to produce the results for cold flow and indeed combusting flow within an internal combustion engine. Okay, so here you can see why I keep saying that this is really cool, because you're going to have complex geometries. So on top left is, let me see if this will click. We are going to have a diesel engine with sets of intake and exhaust stroke with quite a complex geometry in order to create swirl. The one in the middle will be a gasoline engine, again, with quite a complex geometry. This part here is the location of the injector. And on top of all that, you have to deal with the fact that within the simulation, the valves are opening and closing, the piston is moving up and down, and there is really quite a lot of physics to be done. Now, combustion modeling challenges have changed considerably over the last 30 years. And although this looks really pretty, actually we had it easy. This was the very beginning of optical access internal combustion engine, doing lift images of flames, doing measurements of flow structure within the internal combustion engine. And in fact, we knew really little. So the kind of simulations that we could do was a piston going up and down, taking the mass that has been sucked into the cylinder and calculating the maximum pressure with and without combustion. Now, when one thinks about it, I can do these simulations on a piece of paper. And yet I was running pretty sophisticated pieces of code, and people would complain if we would miss the maximum pressure in the system by more than a couple of percent. This is because we knew so little about the system that any insight in terms of the flow structure and, for example, how well the intake manifold works in creating swirl in diesel engines or tumble in gasoline engines really worked. Okay. The other aspect that came to mind is that each of these pictures here was really quite a complicated project. So just building the mesh for one of these gasoline engines or diesel engines with complex port geometries was a job that would take several months. Okay, so in 1999, I wrote a paper at the SAE and I said, with the automation, which is where the pictures come from, we are able to reduce this to several weeks from the time that the new geometry becomes available to the time where you can actually do the simulation. And the response is ridiculous. You can't do it this fast. Now, moving into the 21st century, not only do we need to do better in terms of geometry modeling and flow modeling, but the turnaround of the kind of work that we need to do is orders of magnitude more complicated. Okay, so in year 2020, running a simple combustion model really doesn't work for us anymore. We need to deal with larger dissimulation, cycle-to-cycle variation, NOx, pollutant modeling, NOx, soot, unburned hydrocarbons, and various other things. Now, with Euro 7, this is again becoming an order of magnitude more difficult. So not only that we have to do all these things, but we have to do them more accurately. The only thing that saves us is that, of course, our computers are significantly faster than they were in the late 1990s, and we are actually capable of doing that. But the requirements from the users have also increased beyond measure. So going back to my previous picture, running one of these simulations would, quote unquote, almost get you a PhD. So creating the geometry, running the simulations, maybe doing various changes in load parameters, RPM, and I don't know, fuel injection patterns, and comparing that with an experiment was a 3-year project. What I want to do now is for each of those simulations on significantly finer meshes, I need to perform a detailed parametric study and optimization, which means instead of one simulation that is useful in a certain way, I need to be able to do hundreds of them. This is a new quality because the pure quantity of simulations that we need to do is so much larger. So in fact, the user requirement and the knowledge that we have about the problem move the CFD modeling of complex combustion systems onto a new plane. So how does OpenFOAM come into that game? During my professional work, I have spent about 12 years working with commercial CFD vendors, both at StarCD and at Fluent, which was now swallowed out by ANSYS. And going in, I had a certain set of beliefs, or if you like, illusions about how the system works. These are very rich companies, and they employ very successful and knowledgeable people. However, they are not quite as good as I would like them to be. The first thing is that they still write software, and the software is not an order of magnitude better in quality than the software that's written by other people. If you don't trust me, think about Microsoft Windows from late 1990s, early 2000s, where the operating system spends half of its time on its back, and it was riddled by viruses and other things, in spite of the fact that Microsoft was probably the richest company in the world at the time. So having a lot of money doesn't make you write better software. What makes you write better software is caring about the things that you do. The second aspect where I was somewhat disappointed was the research and development effort that these people were putting in. It turns out that the proprietary part of CFD methodology held by those solvers that we cannot see in source code is not that great. They don't invent better turbulence models. They don't invent better discretization practices. They don't invent better equation-to-equation coupling and then keep them to themselves. And indeed, the complete CFD methodology that they use is already in the public domain. Thinking about it, this is how it should be. Because if a company says, well, I have this secret switch which will make your results perfect, of course, you don't believe them. So OpenFOAM comes into the game because what we ended up doing, it was not the original plan, but it gave a certain set of advantages that really made OpenFOAM competitive. The first one is, it is completely open source. What that means is that if you don't like the way that the discretization is being done, or you choose a different formulation of the energy equation that you would like to solve, you have the source code, and you also have the capability of changing the source code to make sure that it does what you want it to do. So there is no lying. I cannot pretend that I'm doing something that I'm not pretending. And you have the same starting point as everybody else using OpenFOAM in terms of developing and enhancing the capability that we have. So that's an interesting platform, but a platform without capability doesn't get you very far. So apart from that, OpenFOAM provides modeling capabilities in library form for reuse. And if you remember, I talked to you about chemical reactions in internal combustion engines and chemical reactions in fuel cells. And the chemistry is still the same. So I should be able to reuse the chemical reaction interface to do both of these things. And this is great. It is great for the reason that the more a certain piece of code gets used, the better it gets. It's got fewer bugs, it is more robust, it is more reliable, it is more validated, and we all benefit from that. The fourth item on my list is complex geometry handling. In the very early days of my involvement with CFD, we used to have Lego cube types of geometries, which from an engineering point of view are not acceptable. So if you're doing heat transfer and your geometry doesn't represent the actual surface area between the fluid and the solid, you can't expect your heat transfer results to be good. From a purely practical standpoint, in collaboration with industrial companies, unless you show them that you're solving their true geometry, you have no chance of convincing them to go this way. The last point on my list is very interesting. If the software is open source, then we can not only develop it ourselves, but we can collaborate in a way that makes things more reasonable. We can ship pieces of source code from one person to another. We can also share, debug, develop, etc., those pieces of software. And for those professors in the audience, in case you're running industrial collaboration, this provides you an avenue to ship your results to your industrial sponsor the moment they're finished. This is normal, right? Well, it should be, but it wasn't always like this. So in the early days, or in the days of commercially dominated CFD, at the end of the PhD project, you will get a PhD thesis, maybe a few papers and validation cases, but the industrial sponsor would not be able to deploy the results of the CFD on their study within the company. And this is where the true power is. I find that most of CFD work that I do is immediately required by someone. And in fact, they are begging for the answers as soon as the first version of the model is working. So this idea of being customer-driven in model development, in validation and verification, really helps within the story. So how we got there is by design and also by luck. So the idea of OpenFOAM representation in software is that we can take partial differential equations, which are the natural language of continuum mechanics, and represent those equations in the software in the way that we have seen. I believe that by now, a lot of you have seen OpenFOAM. So just by looking at this picture, you can recognize the FVC : grad U being the velocity gradient and FVM ddtk being the rate of change term, which really helps. Okay, now please notice there is no magic happening behind this. The actual implementation of discretization terms, boundary conditions, and all the other things that happen with the system are still sitting beyond that. Okay, as you can see, I am solving individual partial differential equations in the way that I would write them when I develop a new combustion model. Well, this is good, but it is also bad. So the modeling paradigm that we are looking at is this FEM operator-based system that allows me to create a discretization of partial differential equation that I showed you on the previous screen. Once this is working, we can actually combine the terms of the equations to do other things as well. The kind of things that we can do will be structural mechanics or any other sort of problem in continuum mechanics, which takes us away from the arena of just doing fluid flow and heat transfer that we are so. However, within the paradigm of the solution of combustion modeling, this is not enough. In diesel sprays or in coal combustion, we will also require Lagrangian particles. And interestingly, the moment it became available, the surface moment, the surface discretization, where you solve for things like liquid film on the surface, have also come within the framework. So this is now a pretty complete set of numerical tools. I can solve volumetric equations, I can solve surface equations, I can solve Lagrangian particles going through this system, and I can couple all of the things together. Three more things. Turbulence appears in most of the problems. And it turns out that turbulence for combustion is not very different than turbulence for other types of compressible flow. So we can extract the physical modeling of turbulent phenomena into libraries and use them separately as well. And that, of course, involves both RANS and alias capability, but it doesn't quite stretch to DNS because DNS will be a different kind of problem. I have also spoken about the interface to the chemistry modeling library. Okay, that one is important and we will revisit it later. Now, there is a further problem that we need to discuss. If you look at the way that the system is set up in my partial differential equations, if I have multiple equations sitting next to each other, the language that I am representing here is not quite complete. I would like to be able to deal with the solution of K and omega within the system of partial differential equations, where K and omega depend on each other. But based on the kind of things that I showed you so far, it is not immediately clear how to do that. So that leads me to the topic of the segregated solution algorithm. Equation segregation is a really old idea. It comes out of 1970s. And the principle at the time was that the computer power, memory, and CPU speed was so limited that I could barely solve equations one at a time. Therefore, we had to invent things like simple and piezo in order to couple the pressure and the velocity. The turbulence equations would be segregated from the system. The combustion equations could expand the system. So whatever we did was basically to solve multiple equations one at a time, and then handling inter-equation coupling via outside loop, which basically means keep repeating the same time step, updating the properties until they stop changing. Is this a good way of coupling? Well, not necessarily. It depends whether the transport is more dominant than the cross-coupling through the source terms. And if it is, then you're fine. But if it isn't, it might not work at all. The thing that it is very flexible. And it allows us to expand the system of partial differential equations. For example, to the transport of multiple species within the chemical reaction mechanism, or adding radiation models, turbulence models, conjugate heat transfer models, etc., and just performing outside iteration from the system. So within the framework of OpenFOAM, you can really assemble very large, complex, nonlinear, coupled models of partial differential equations, wherever they come from, and solve them successfully. Sometimes it is not going to work, like, for example, in nuclear reactor neutronics, but that is beyond what we are talking about today. Okay, so let us imagine it is the year 2022, and you have access to the code that can do combustion modeling. What are your practical requirements in terms of doing combustion simulation? Well, life is much more complicated than it was in 1990s. The first thing I already mentioned, which is the complex geometry support. Within the mesh, you should have the ability to capture the real geometry. And just the very next step, dynamic mesh support, meaning that in an internal combustion engine, the piston will move up and down, the valves will open and close, you will have various parts of the system working with each other. And in the end, you will very quickly require adaptive mesh refinement. This is basically to allocate your computational resource in the best possible way. The second thing that you need is the possibility of dealing with high performance computing. Well, this is a non-trivial problem in its own right. But for example, Professor Ng in our audience has access to a computer with 200,000 cores, and he most definitely wants and needs to use the whole of it. So if your software is not capable of being scaled up to exaflop performance, it really isn't good enough. The other problems are much more serious. For example, model validation and verification. This is a huge problem because for every hour of new physics model development, you're going to waste hundreds of hours on validation and verification against experimental results, because the quality of matching numerical results to the experimental data and robustness of this process is really critical. And remember, one CFD simulation is no longer enough for you to do your PhD project. You may need tens, hundreds, maybe thousands. Recently at Chalmers University in Gothenburg, I spoke to Professor Håkan Nilsson, and he told me that for one master project in hydraulic simulations, he spent 73 CPU years of CPU time for one student. Wow. Okay, so this is the kind of environment we have to have. The last requirement should also not be underestimated. The software needs to be so simple and robust that it can be developed by PhD students. They best work in groups. We should educate, train them, support them, etc. But the reality is that most of these people are not professional programmers, and doing things in the way that allows them to do this well is not easy. So let's go back in history. Okay, so here I pulled out a book called 50 Years of CFD Engineering Sciences, which is a commemorative volume published in memory of Brian Spalding. It is possible that you haven't heard of him, in which case I need to ask you to do your Google search and do your reading, because Brian Spalding is one of legendary professors, and he is the founder of the thermofluid section at Imperial College London. And basically, most of the stuff that I know from CFD was either done by Brian Spalding first, or he was involved in it in some ways. I will start with a loose quotation because I cannot find the actual real quotation. And this is what he said in terms of combustion modeling. We have to overcome the artistic aspects of modern combustion modeling. This is circa 1960, and study the problem from principal aspects of conservation of mass, momentum, species, and energy. Okay, so what this says is your combustion modeling is not an art, it is a science. For those who would like to know more, below on the screen, you have the link to the book, which was written by some of his students, notably Norberto Hrvoje. I think he was his last student at Imperial College. And unfortunately, Brian retired before I joined, so I only got to meet him afterwards. So what did this guy do? Okay, 1951, PhD thesis, University of Cambridge. First numerical simulations, 1954. Fundamentals of combustions, CFD calculation of recirculating flows, 1968. Numerical prediction of laminar flame propagation, the eddy breakup model, which is criticized over the last 20 years in a million different ways. But take a look at the year, 1971. I will not go through the rest of the list, just point you to the last item, 1995 multi-fluid models of combustion. Okay, so as you can see, from 51 to 95, he was either leading or driving forwards the combustion model. Why am I bringing him up here? The first reason is that the complexity of modern combustion modeling required his entire career. And the second reason is one saying that he had towards the end of his career, which says that within CFD, you can either have complex geometry or complex physical modeling. And you should not attempt the two together. So if you have complex geometry, you better concentrate on doing external aerodynamics on the real shape of a Formula One car, because the fluid flow model is trivial. And if you're doing combustion, your physical model is so complicated that in reality, you should limit yourself to simple geometries. Well, guess what? We are trying to do the exact opposite. Complex physical model on complex dynamically moving geometries, which is quite a challenge no matter what framework you're working. Okay, so let's start talking about combustion modeling after this interaction. And as you have seen, my first picture is actually a diesel spray in a simple geometry according to Spaulding. So in order to do this, it is no longer enough to have the capabilities of the finite volume method, discretization operators, mesh, and all the other bits. But we need to build up intermediate layer of OpenFOAM as a computational continuum mechanics library. And the first one of them is the Thermodynamics Package. So the chop of the Thermodynamics Package is to associate the material properties of the medium as a function of state variables. In my case, that is typically pressure and temperature, but I'm sure Professor Fitzner, during his career, had different choices for different reasons. So even this first point of what are my state variables is not fixed. The second problem that I have is that for each property, like laminar viscosity, I may have different levels of approximation with different levels of accuracy. So I can start doing my simulation with constant, I don't know, thermal conductivity or specific heat capacity. And as I'm getting towards doing comparison with experimental data, the effects of variable specific heat capacity may become important. So I need to be able to switch between them quite easily. The third problem is the dreaded energy equation. Why don't I like it? Because it can be formulated in many different ways. Internal energy, enthalpy, thermochemical energy, total energy, and they both deal with the association of my basic state variables and material properties. Now, every time you have a choice means that we don't know enough about the problem, or that the correct choice depends on the kind of problem that you're solving. So sensible enthalpy may be perfectly sensible in some cases, but if you're doing high-speed reactions and you're worried about the stability and accuracy of your solver, then solving for total energy may be much nicer because the equation doesn't have source term. So again, I need to give the capability of changing the details of the interface. The last point is that the interface between the thermodynamics library and the rest of the flow solvers is different. I can have density-based solvers where I calculate the fluxes directly. There I need the density. I can have compressible pressure-based solvers, incompressible pressure-based solvers, and they all need to couple, quote unquote, conveniently to my thermodynamics package. So what my thermodynamics package does is it is responsible for the thermodynamics state of the mixture and evaluates material properties such as rho, Cp, Cv, and it will update those properties based on the state variable. Easy, right? Well, no, it isn't. Because while all of this is happening, I am also going to have chemical reactions changing the local composition of my material. So the interface is very deep, and doing the conversion, for example, between enthalpy and temperature to enthalpy, sometimes requires iterations. And for all those who have attempted to do combustion simulation with OpenFOAM, I'm sure you're familiar with temperature getting out of range or TO or T to H conversion failing. Well, typically this is not the fault of your thermodynamics package, but something else has gone wrong in the solver, but it is the thermodynamics package that does the screaming at you. So have a last look at what is all of the stuff that I need to have in my thermodynamics package. Starting from the bottom, I can have an equation of state. And to make things simple, I'll just say perfect gas. 5 seconds later, I will say, no, I want it incompressible with constant density, with variable density. I want a real gas, etc. So there is a whole bunch of choices. The second level is the species composition of the material. The third are the thermodynamics properties of each of those species, plus the mixing roles for thermodynamics and for the transport properties. And then I'm going to start dealing with the mixtures, okay? And those mixtures can be, again, be packed up in many different ways. Did you notice something? It's getting hard to follow all this. And for this reason, this is the most hated and the most changed part of the code, because whatever you write is always a compromise between what can happen and what should happen, and something which is convenient for some people, but not convenient to the others. Suddenly, the idea on working on discretization operators or high performance computing actually makes my heart smile, because the job of dealing with thermodynamics library is so much harder. Things get even more complicated, and that is the support for chemical reactions. Okay, so in order to do combustion, we need to account for chemical reactions. And again, the choices of reactions are multiple, with each of them operating in a different way. So here we are going to have transport equations for individual species. And then we are going to have the reaction rates saying what sinks and source terms are working within the system. So this part of the code looks good, and it will allow me to do the kinds of things with the mixture, and yet I'm still unhappy about it. The basic unhappiness on my side comes from the fact that the chemistry modeling package deals with temporally changing sources rather than long-term equilibrium. So everything's been designed to do transient simulations. And if I'm looking for steady state operation, then my thermodynamics chemical reaction support really doesn't do it for me yet. Okay, so this is a big to-do, but at least we know a clearly defined interface, because dealing with chemical reactions is about an order of magnitude easier than it is to deal with a thermodynamics library. Notice, there is a lot of code here. There is a lot of capability. The interfaces are complex, and it really only got me a few steps towards being able to do combustion. But it also saved me the need to keep re-implementing all of these interfaces to ordinary differential equation systems that solve for chemical reactions. Right, so now I can solve volumetric equations of conservation of mass, momentum, and energy. I can solve transport equations for multiple species. I can deal with heat transfer. I can set boundary conditions. Let us assume that I am going to do complex geometry as well. Let's model combustion. The bad news is that there is no such thing as a universal combustion model. In fact, there is, but if you choose that one, you're never going to get to the proper performance and accuracy of results that you need. All of the combustion modeling is basically to do with the chemistry, but the difference in the scales between the speed of chemical reactions and the speed of mixing influences the approach to the modeling that you use. So if I choose to do, I don't know, an internal combustion engine in a gasoline engine or a high pressure gas turbine, doing the chemistry will be truly problematic because the reaction zones are so thin that I can't afford to have enough mesh resolution to happen in there. So let's just jump into the details of how combustion modeling is modeled. Now, here I have to say that I am not an expert, and there are people in the audience who know more about it. So I hope you will correct me in the questions and answers later. Conceptually, my first approach is, let's do a detailed chemistry solution. We are going to specify chemical species for gas composition, chemical reaction that take place, run the system, and we are going to get the answers. The second opposite of this is that in some phenomena, the speed of mixing is so slow compared to the speed of chemical reaction that I can assume that my flame is a thin surface in space. So this is called the Flamelet approach, where I'm going to separate my fluid into the burnt gas and the unburnt gas, and I'm going to represent the chemical reactions in terms of laminar and turbulent flame speed, and then run the chemical reaction set in this infinitely thin interface between burnt and unburnt. Both of these are basically sets of volumetric equations, so I don't have to worry about too much. In diesel combustion, I have to take care of the fact that the fuel is being introduced in a liquid form. So in order to perform the combustion in the gaseous state, my liquid needs to be converted into gas via fuel evaporation and mixing, which basically controls the combustion. So this approach takes us back to the 1990s and the early picture that I showed you, where the droplets are represented as Lagrangian particles, exchanging mass, momentum, and energy with the continuous phase and preparing the mixture, and the combustion reactions are now much simpler to model because everything is controlled by the mixing. To complicate this a step further, in coal combustion, I am going to have one additional phenomenon. Apart from the fuel, which is provided in terms of solid particles releasing gases into the continuum, there will also be a combustion reaction on particles themselves, which then needs to be taken account within the combustion model. I'm sure there are many other things that I should have said here, but for the purpose of this presentation, let us just consider that based on the choices that I have given, you will be able to pick up the modeling paradigm which is appropriate for the problem that you're solving. So let's take a look at them one at a time. All of these things need to be validated. Working with my colleague Dominic Christ, we have done extensive validation of Sandia Flame D, which is one of the test cases where the chemical reactions mechanisms and flame can be tested with excellent experimental results. So the picture that you can see here, maybe there is a movie as well. Okay, shows you the temperature and the oxygen concentration within the flame of Sandia Flame D. The mechanism that we are using has got 53 species and 325 reactions. You remember what I told you about the segregated solution procedure? So now, apart from pressure, velocity, energy, turbulence, I have 53 additional transport equations. And the detailed mechanism consists of 325 reactions, which means that my ordinary differential equation solvers need to do a pretty good job. This is a lot. At this level, the cost of the simulation is actually moved from the three-dimensional fluid flow into the ordinary differential equation solvers handling chemical reactions and evaluation of properties using, I don't know, Janaf lookup tables, which require complex polynomials. When stuff like this is used in an industrial environment, the turnaround time is critical. So dealing with this requires changes in the implementation on the ODE solver and material properties side in order to speed things up. There is, of course, another way of speeding things up, which is necessary if you try and do a more complex geometry. So here I have a thermal power plant steam generator where we are modeling the similar aspects of combustion in a similar way. But instead of using the full GRI mech mechanism, we have two different approaches. The first one is the four-step chemistry, and then using the extended Zeldovich mechanism to calculate NOx, which was the point of doing the simulation, compared to detailed chemistry modeling with the GRI mech mechanism that I showed you on the previous slide. So if you look at it, this is a very pretty simulation involving heat transfer and various other aspects that are built into the steam generator. But from the point of view of CFD, this is not too terrible. The results look pretty. I was surprised how accurate our NOx predictions were. And we found out that this is because our mesh was really fine. So this is a 7 million cell mesh, and it ran for about a week on 120 cores of a parallel computer. In contrast, the GRI mech mechanism was never properly completed because the CPU time is still quite large. Now, looking at the picture of this thing and thinking about the saying from Brian Spalding. Where are we? He said you can have complex physics in a simple geometry, or you can have simple physics in a complex geometry. And what we have here is a reasonably simple geometry with a reasonably complex physics, and things work well. So let us move to the next set of examples. And here I only have one. Okay, so for the Flamelet modeling approach, with premixed and partially premixed, we have done quite a lot of simulations. And I'm only showing you this one example. Again, there may be a movie. Because the point of running a case like this is that we are no longer interested just at looking at the steady state, like we did in the previous simulation. In this case, with the backward-facing step, there is going to be an interaction between the turbulent premixed flame and coherent structures in the flow, which will cause the flame to flap about. So suddenly, rather than looking at steady state, we need to take a look at the instability modes that we need to have within a regime like this. And because the combustion model is relatively simpler than it was previously, this kind of simulations can be done reasonably today. Further, the difference between the cost of RANS simulations and LES simulations is not that large. You're not interested in the near wall behavior, so it can be wall modeled LES. And in order to make your combustion model work well, you need to have a relatively fine mesh. So just by putting in a lot of cells and running a simple Flamelet model within the framework of larger simulation, we can answer a lot of requirements. I'm not showing you any more of these because later on we will have some examples of internal combustion engine modeling, and quite a lot of that uses the Flamelet approach, so I'm going to save my time for later. What about diesel combustion? Well, we have all of the things that we had before, but now the Lagrangian diesel spray model need to come with a complete set of submodels. From the injection, we need to introduce Lagrangian parcels within the systems, run primary atomization, turbulent dispersion, collision, drag, droplet evacuation, and heat transfer model, and then run some sort of combustion model in the volume. So the Lagrangian particle library written in OpenFOAM is available, and it's got the entire set of capability that I listed here. But I'm going to concentrate on this last item here, droplet wall interaction. Okay, so what we have here is another set of problems that come from the point of view of modeling where you have the interaction between the Lagrangian phase and the wall. Well, we never had that one before. So let's just look at some pictures of what this looks like. Okay, so again, with some luck, there is a brief video showing the injection of particles. As you can see, the drag between the continuous phase and the discrete particles will form the shape of the jet. The particles are colored with their temperature, and as the temperature increases, they will start evaporating, and after a while, I'm going to start burning in the volume to go through the system. Okay, so here again, we are within the framework of what Brian Spalding was talking about, which is more complex physics now. In fact, quite demanding complex physics, but my geometry was simple. You can take this further by looking at different kind of Lagrangian particles, for example, in coal combustion. So the set of pictures I've put here will show the same layout, but for coal combustion. And this one has been applied to a blast furnace which is a very different environment from the one that I started from. But because all of the aspects of the modeling are still here, it is possible to do this simulation to a relatively good standard. Right. So far, I didn't bring you even close to the pictures that I showed you on the early slides, showing you internal combustion engines, where the piston and cylinder and the valves would be moving up and down, and you would be able to do all kinds of phenomena related to dynamically changing geometry. So let us just say a few words about how the polyhedral mesh support and dynamic mesh allow you to marry complex geometry with complex physical models. So historically, CFD meshes were using a shape-based support. And one of the big things done in OpenFOAM was to use a polyhedral mesh support class. One can recognize that the principle of the finite volume method is that we are writing conservation equations over a piece of space, limited by a set of flat faces. Nowhere in the formulation does it say that your control volume needs to be a hexahedron or a tetrahedron. Now, hexahedrons are good, but the problem of mesh generation is just as hard as the problem of doing complex physics modeling. And the idea of polyhedral mesh support is that we are going to boil down the finite volume method to its very basics and provide ultimate freedom in the way that you generate the mesh. So the mesh generation today still hurts. Building meshes for large complex geometries will take hours, sometimes days. But by changing the rationale of the way that the mesh is being built has got some consequence. The first one is that all algorithms need to be fully unstructured. Okay, so that means discretization of convection, diffusion, source terms, sink terms, boundary conditions. Any problems there? Well, no, that has been solved in late 1990s and early 2000s. But how about radiation? Well, if you're doing ray tracing, that may be a bit tricky. If you're doing Lagrangian particle tracking, that may be even more tricky, especially if you cannot guarantee that all the cells are convex, and you cannot. So the consequences of polyhedral mesh support are really nice, but the more important aspect of polyhedral mesh support is to be able to deal with dynamic meshes. So the idea of dynamic mesh is that the geometry of your mesh changes in time, and unlike the moving deforming mesh, this change in geometry cannot be described simply by moving the vertices of the mesh. So a topological change is the change in the structure of the mesh where the number or connectivity of points, faces, and cells changes during the simulation. Okay, and here are some examples. Okay, so we can have internal part of the mixer vessel rotating relevant to the external part, or on the left-hand side, we can have a layering, creating and destroying the layers of the mesh. I will click on this with hope that the movie is going to work. Okay, it is a bit too fast. Let's try again. Okay, so what you can see here is that as the mesh is deforming, the number of cells is changing within the system. Well, that's great. It's also unusable, because if I want to define the changes in the mesh on the level of cell number 73 changes in time step number 525, this is completely unreasonable especially under the constraints of high performance computing and parallel processing. So on top of my dynamic mesh, I need to introduce a set of ideas where the user can define the changes in the mesh by saying, this is an internal combustion engine. It has got a piston and a valve. As the piston is moving, the mesh structure needs to be changed accordingly. One more philosophical point at this stage. On one side of my system, I am going to have the CFD solvers, solving, I don't know, Flamelet type combustion set of partial differential equations with the possibility of changing the mesh in space and time. On the other hand, I am going to have an internal combustion engine where the mesh structure changes because of the motion of valve and piston. But also, I could run the same solver in a gas turbine and use adaptive mesh refinement to change the mesh. The point is that the mesh changes on one side and the solver that accepts those mesh changes are separate from each other. And because the interface between them is clearly defined, meaning, dear mesh, change yourself, I don't care how. And dear solver, the mesh has changed, this is how the data has been mapped. I can actually afford to do these kinds of things within the framework of the same software. In CFD, one doesn't do the best of one's work on their own. And here I will use the opportunity to advertise one of the future talks by my friend, Professor Tommaso Lucchini from Politecnico di Milano. And here are some movies showing the kind of simulations that they can do. Okay, so what you can see now is spray injection. Okay, within the mesh with the piston moving at the same time. I also promised you some adaptive mesh refinement. And here is one of the early simulations of Lagrangian spray using error-driven adaptive mesh refinement in the system. Okay, this is now maybe 10, 12 years old, but it shows how the combination of tools and the combination of effort within an open source environment brings excellent solutions. Right, you remember at one stage of the system, I spoke to you about spray-wall interaction. This was one of the CFD projects that was run at the group of Professor Gossman in 1990s when I was there. And Cheng-Xin Bai was looking at the phenomena of a droplet hitting a surface and then either sticking on the surface, evaporating slowly, flash boiling, bouncing, etc. In reality, there is one more degree of freedom that he didn't look at, and that is whether the surface is wet or dry at the beginning of this process. So as an example of collaboration, talking again with our colleagues from Politecnico di Milano, we have introduced the idea of the finite area method, which solves for the surface phenomena. And probably the most important of these surface phenomena will be a liquid film. In this case, the spray hits the wall, it wets the surface, the shear can drive the film up and down, and the film is subject to heat transfer, which means that it can evaporate based on the state in the gas above it and on the metal underneath. So the moment we deployed that in a completely different paradigm, the colleagues in Milan said, well, this is exactly what we need. And the first simulation resulting from that collaboration is shown here. So you have a gasoline engine with port injection and a large number of droplets aimed through the gaps in the valve. And what you can see here is how the wall gets wetted, okay? And later on, various other parts of the wall will be wetted as well. And the system of mixture preparation will now account for all the bits that we can capture within this volumetric Lagrangian particle surface wall film framework. The reason why I'm showing you this is, number one, because it is cool. And number two, because it illustrates how having a full set of numerical discretization support allows you to evolve and develop your physics model in order to do the kind of things that you need to capture the real physics that goes in the flow. And notice, physics is not nice. It will do what it thinks to do rather than things that are easy to model. Of course, within the concept of automotive applications and combustion modeling, Lagrangian spray, mixture preparation, there is a million more things that we should talk about. For example, primary jet breakup, which was done in collaboration with Professor Im at KAUST, issues of diesel particular filters, catalysts, and various other phenomena, which extend the kind of things that we have done. But now I'm really getting tired and we are past 1 hour. So let's just finish this with a quick summary. So the basic design decisions in OpenFOAM make it easy to implement loosely coupled sets of partial differential equations of the type seen in combustion modeling. The inter-equation coupling is typically handled using a segregated solution method, which makes it easy and simple to extend, but sometimes it can suffer from equation to equation coupling. If you get to those problems, within OpenFOAM, we have other ways to strongly couple region to region and equation to equation. And that is something that we need to consider. OpenFOAM is interesting for combustion modeling for 3 reasons. The first one is multiple discretization support. Lagrangian, finite area, finite volume, and conjugate couple simulation before all of them. The second one, the hard work of dealing with thermodynamics and chemical reaction package has already been done, and I hope it is done in a way that makes it relatively easy for you to interface with. And finally, the solver has got all the bits that you would expect from the modern CFD solver in the year 2020, like high performance computing, dynamic mesh support, adaptive mesh refinement, etc. So I hope this will inspire you to consider the way that OpenFOAM supports your combustion modeling work within the framework of open source, where we can share not only results in terms of papers, but also actual software implementation and source code validation, verification results within the community. There is 2 more things that I need to mention here. The first one is OpenFOAM Journal. This is one of the new initiatives within the OpenFOAM world, where we have decided to set up a journal which is free to publish in, and it is free to read. It is funded by a small number of companies and volunteers, and it allows you not only to publish your work, but also to provide the source code of the things that you need to do to show off your capability. The second thing that I need to mention is the OpenFOAM workshop, which is run this summer at the University of Cambridge between the 11th and the 14th of July. And if I cannot see you live, please consider attending virtually so that we reach out to the community that exists worldwide. And finally, I told you about training. Over the last 15 years before COVID, I was running the NumUpFoam summer school, where we would accept about 15 OpenFOAM users and developers in their late PhDs or postdoc career stage, and do the best hands-on one-on-one training that we could over the period of 2 weeks. I am planning to run one of these summer schools at Cambridge this summer in September, and a formal notice will come soon. Thank you, Professor Zhang, for letting me talk as much as I want to. I thank you all for your patience and your attention, and I'd be happy to answer your questions.
Okay, thank you very much, Professor Jasak. So before the Q&A session, maybe we have 2 minutes break. Okay, is that okay, Professor Jasak? Okay, yeah. So for the audience, if you have any questions, you can submit through the chat function or Q&A function. Okay. Professor Jasak, are you ready for Q&A?
Yes, I am. Please have a look, because there are Q&A and chat questions as well. So pick both of them, please.
Yeah, okay. So may I first check if any panelists have questions? So if you want to ask, you just open your microphone. Okay. Professor Yin, do you have any questions? You just mentioned.
Well, yeah, it's a great overview. Thank you very much. Yeah, this is Hong Im at KAUST. Yeah, we have some other ongoing collaboration going on, so I'm kind of familiar with the direction. But I think the entire world is in the modeling world, especially including combustion modeling. I guess this is more of a comment that the people are embracing more and more of the machine learning tool. Specifically more on the artificial neural network paradigm to in the various aspects of the code to enhance the performance as well as the enhance the discovery part. So I don't know if there's any kind of a roadmap in this OpenFOAM community to have those parts available. I understand a lot of these ANN tools are already independent package by itself, but should we make any extra effort to integrate them together as part of all this effort?
Thank you, Hong. Okay, so from my side, there is no roadmap because I am still learning about it. What I see is that just using artificial intelligence and machine learning within the framework of such strong systems with conservation equations governing possible solutions is not as easy as it is in insurance or in finance. So within the framework, there is a set of projects at University College Dublin, which are using artificial intelligence methods in solid mechanics. But I am personally not involved. There is a story about setting a special interest group within the level of OpenFOAM governance to enhance collaboration on this. And if you're interested in working in that direction, I promise to support you, and it would be great to start the initiative. Thank you. By the way, I think there are hands raised in the audience, so maybe you can go through them.
Oh,
Yeah, okay.
maybe I will go. Professor Jasak, and thank you for the very interesting presentation. And my own team has been benefiting from OpenFOAM since 16 years ago. So a big thank you to you, to the pioneers, to David Gaussman for having you and Hrvoje as his student. He was also my first employer. Many thanks. But I think, in my view, OpenFOAM, despite all the advantages, it faces a big challenge. It's to scale up. So I did put this question in the chat. Do you have any reason how can we meet this challenge?
I not only have a way, I also have the money. Okay, so there is the ExaFOAM project, which is a 3.5-year European Union funded project, where we promised to move the code onto exascale computers. This is not an easy challenge, and it will require fundamental changes in the code, because some of the design decisions are no longer going to be the same. For example, carrying all boundary patches on a 100 processor is not a problem, but on a 100,000 processor, it is a problem. Decomposition and reconstruction, code profiling, and quote unquote primary and secondary algorithms. So what we learned so far is that the basic machinery of the finite volume method works really well. So matrix assembly, calculation of the fluxes, calculation of the source terms actually scales to hundreds of thousands, of course. What does not scale are linear equation solvers. And my role within the project is to look at the next generation of linear equation solvers, which will go to those extremes. Interestingly, there is very little that is already being done in terms of demonstrating parallel scaling in implicit linear algebra to 100,000 CPUs. So we're looking at new algorithms, new preconditioning types, new types of algebraic multigrid solvers, and there is hope. There are also obstacles. Running adaptive mesh refinement on 100,000 cores is more demanding than running it on 1,000 cores. And issues such as dynamic load balancing and load redistribution also become problematic. The final challenge is that these exascale and petascale machines are not really well defined, meaning that every new machine is going to have a slightly different structure. Balance between local to cluster to global communication is going to be different. And I think we have a lot to learn. So to finish on a positive note, we are aware of the problem. There is a group of about 16 partners working on it, and we will report on that on the OpenFOAM workshop in July. But I don't think the problem will be solved within a single project, because it hasn't been solved with any of the implicit CFD codes of today. I hope I answered your question.
Yeah, thank you. Thank you.
Okay, thank you. Zhichen also raised a hand. So you may want to ask about yourself, right?
Okay, can you hear me?
Yes, very clear.
Okay, let me see. I want to show my face as well. Oh, okay. Anyway, thank you so much, Professor Jasak, for this great talk and your generosity of creating and sharing OpenFOAM. And we all owe you a great deal. I want to ask your comments on a few questions which I receive when I present my work using OpenFOAM in my combustion community. The first one being, The numerical discretization is limited to second order, as far as I'm aware. And the second order time scheme is close to
Okay, I hope Professor Chen will come back. If not, I can start answering with this part of the question.
Hello, hello, Zhi, can you hear me? Okay, because I can see the question, maybe I read on behalf of him. This is also okay, right? Yeah, his first question is the numerical scheme. Numerical discretization is limited to second order, and the time scheme is also second order. So he wants to get some comments from you. This is one. The second one is the parallel scalability. He believes OpenFOAM is actually very good on this aspect, at least for his experience so far. And the last one is the row pimple algorithm isn't really compressible. So could you make some comments on these three questions? I guess he was asked by some reviews.
Sure. Okay.
Yeah.
You may have to remind me of the question. So let's start again from the beginning. Second order finite volume method is the technology of the 1990s and early 2000s.
Okay.
It is very robust. It works really, really well. It scales really, really well. And it is terribly difficult to extend. Okay. So here I have the project with partial funding, but the effort is substantially larger. The way that we are going is the discontinuous Galerkin discretization of arbitrary order in space and time. Okay. Up until 10, 12 years ago, this didn't work properly, at least in my opinion, because we could do explicit density-based solver, but solving implicit Laplace equations and pressure velocity coupling in the way that we are used to simply wouldn't work. Now it does. I have personally been working on development of block matrix solvers on the linear algebra side. And there is a formulation of this continuous Galerkin, which is element-based. It was developed at Technical University of Darmstadt, and we are looking to implement that. Okay. It will be implemented in operator form. It can be solved. It parallelizes well, and it looks beautiful. Okay. However, keep in mind the cost. For one cell in second order, instead of one variable, you're going to have 9. And in third order, you're going to have 27. Okay. So that means that the matrix is 27 by 27 times larger than the scalar matrix. And what we are hoping is that the additional effort of solving such large matrices will pay back the work that we need to do. There are caveats. If I choose consistent third or consistent fourth order discretization in space, then the whole system vectorizes. If I choose local P adaptivity, it does not. Okay, so the cost could go up by another factor of 5. And I don't know which one of these is worth it. Okay, we are currently in the process of developing and testing this, but I would need much more support, both from the community and from industrial partners where we need this. Now let's talk about how desperate we are. So if we are solving problems like acoustics or high accuracy large eddy simulation, I am sure that the benefit of consistent third order space and time discontinuous Galerkin will be substantial. If you're doing a diesel spray combustion in an internal combustion engine, I'm not so sure. Because just by running 10, 15, 20 million cells instead of 1 million cell in the combustion chamber may actually give you more benefit in spite of the fact that the method is only second order, because you can just add as many cells as you can. So my advice is, number one, let us all push towards consistent, discontinuous Galerkin extensions to the finite volume method. And number two, let us go through validation and verification so that we can learn when these higher order methods are really the best way forward and not just pure showing off. One more thing to say. The moment you say, I want the fourth order discontinuous Galerkin consistent discretization in space and time, you will also tell me, I want it with polyhedral support, I want it to run in parallel, I want it to scale to 10,000 CPUs, I want Lagrangian particle tracking, which is consistent with it, I want, etc., etc., etc. Oh my God, that's a big job. Thank you.
Okay, thank you very much.
There was a second and the third question as well, right?
Yes, let me have a look. Okay, so the second one is the parallel scalability. So yeah.
Okay. Recently, I looked at the report from ANSYS saying, oh, we have a wonderful parallel scalable large eddy simulation code. It scales to 10,000 CPUs. Guess what? They were using an explicit density-based solver in an inappropriate formulation because it scales well. Okay, so scaling is a big problem, and it's like watching a baby grow. What you do is you fix all the problems that are keeping you down, and you keep fixing problems until the problems become so big that they are unfixable. So I think over the next 5-6 years, we can improve the scaling, but at one point we have to rely on the hardware. One of the things that I learned is that within the concept of exascale, I always worried about global communication, saying if I need 100,000 CPUs, I cannot wait for them to speak to all CPUs between them in a global reduction and broadcast technique. Guess what? This is not true. In fact, they built the hardware specifically to do these operations with minimal overhead. So it is global communication that scales properly. And we need to learn by working on these machines and finding out which parts of the algorithms work and which don't, which means constantly adapting the code and the choice of algorithms to do the right thing. There are some things that don't scale properly, like, for example, liquid film. Because if out of 100,000 CPUs, you have 5,000 CPUs that contain pieces of liquid film, and the rest don't, then we're stuck, okay? But those are just sort of real-life limitations that we can't work against. There was also a third question, I think.
Yeah, the last one is low pinball algorithm isn't really compressible. So you have any comments for this?
I do. Okay. So when I speak to, now in my group in Cambridge, there is Professor Nikiforakis, who works on density-based schemes, and he will use approximate or exact Riemann solvers in order to solve problems like 4 states of matter, or shocks waves in plasma, etc. And he would call his algorithms really compressible, and he's right. The raw pimple algorithm deals with compressible flows, and the only thing that it really doesn't have is it cannot impose the entropy condition. And that's because when I'm doing an internal combustion engines or I'm burning a diesel spray, the entropy condition within the coupling of rho and E doesn't really matter, and I can survive without. On the other hand, the algorithm is good enough to capture density variations in the flow in an appropriate manner. And as a professor of turbomachinery, I can tell you that we are doing compressibility effects in compressors, gas turbines, and other things, and it works fine. What are the consequences? Compared to the solutions by Professor Nikiforakis, my shocks will be a bit too thick, and they may be slightly at the wrong place. Okay, which means that with these algorithms, I'm not going to calculate the drag on a transonic wing, but the performance of a compressor or compression, expansion, and internal combustion engine will be perfectly fine. Okay, so yes, the algorithm works. Yes, it has been validated. Yes, it is not perfect, but it is 1,000 times faster than other algorithms that do the job. So we have to choose the kind of things that we need to do. I'm sure Professor Fitzner will not agree with me, but then again, he's working on high-speed combustion in rocket engines, which is a different problem than the one that I'm looking at. Okay, well, thank you for that. I think you have plenty more questions in the chat, so let's try and address some of them.
Yeah, so the next one is about the any plans to port to GPU, asked by Zhi as well, and I also Yuri Wright from ETH. So any plan for the GPH,
okay.
GPU? Sorry,
I tried GPUs between 2012 and 2014, and what I found is that the balance at the time wasn't good enough because moving things between CPU and GPU costs too much money for them to be useful. The only true way of applying GPUs to CFD is to move everything onto the GPU. So that means that the entire finite volume method operator set would be discretized on the GPU. And that means that we cannot deal with indirect addressing. Okay. Indirect addressing is the basic principle underneath the polyhedral unstructured mesh. Okay. So maybe 2 years ago, my answer would be, I'm not interested. However, within the framework of the ExaFOAM project about high performance computing, we looked at alternative matrix formats that would work for an unstructured polyhedral mesh in order to get improvements in performance. One of these formats actually works with a GPU. So there is a possibility of moving the entire finite volume method library to work on the GPU for an unstructured mesh, but I haven't tried it yet. If somebody in the audience has the effort and the funding and the money to try and do this kind of research, please speak to me. I will give you my ideas because I don't have time to chase this one on my own. If you have money to do some collaborative work, that would be even better.
Okay, thank you very much. So the next one is when does OF can provide a solver that can simulate the extreme compressible combustion, such as detonation, not using the simple and the pinpoint algorithms? So although many researchers are developing their own solvers, so we would like to see the relevant solvers provided by the official version. Okay.
Well, official and non-official is always a problem. Professor Fitzner has got a solver like that. It is great. He has now retired. I don't know who has taken over the group. There is more and more interest in providing this. And what I typically see is that ESI OpenCFD release line will release those when there is industrial interest. Okay. With Foam Extend, what I do is I work in collaboration with people. And if they provide the solver, I will do what I can to distribute it. The good news is that I'm also on the OpenFOAM governance committee and that I speak to ESI OpenCFD on a regular basis. And we are looking to integrate the work as much as we can. Okay. This takes time, it takes effort, it takes validation and verification. There are no obstacles. And if somebody has got a solver like that and they are prepared to share it, we can do it immediately. On my side, this is another job and another effort and another time constraint, etc. So yes, I would like to have one as well, but not quite as much that I would write it myself.
Okay, thank you very much. So the next question is, in Eulerian Lagrangian two-phase flow simulations, the choice of mesh size is very important. So a fine mesh might lead to simulation crash, as the mass of a Lagrangian particle could be much larger than the gas mass in the local cell. So a coarse mesh is not able to capture the Eulerian flow accurately. This issue is more significant in high-speed injection. Is there any solution for this issue?
I think there is, and I have already run 2 projects along those lines. Okay, so the problem describing the issues of Lagrangian modeling on a coarse mesh and a fine mesh is exactly right. This is why Lagrangian was so great in 1990s, because we couldn't afford a fine mesh anyway. I don't think this problem can be solved. It is a fundamental problem of Lagrangian particle tracking. So in recent projects, what we are doing is we are moving to multi-fluid Euler formulation for the spray. And we are currently using a method of classes to describe the spray. And you can have as many as 200 or 250 classes to show the distribution. And this model is fundamentally healthier than the Lagrangian dispersed phase model. Okay, it was developed and used by AVL in, I think, AVL Fire, and we know that it works. Within the context of OpenFOAM and diesel spray modeling, this requires quite a lot of work, and I'm hoping to be able to carry on funding this this all Eulerian polydispersed modeling approach to diesel spray.
Okay, thank you very much. So because of time limitation, we further look at 2 questions. Okay, this is from George Xu, I think in Singapore. Okay, could you please illustrate more about the challenges and the computational cost for adaptive refinement, in particular in parallel computing? Yeah. Okay,
maybe you've seen my PhD. It was about error estimation and adaptive mesh refinement. I did the work in 94 and 95, and my conclusion was that it doesn't work. The reason was that in that time, the meshes were so coarse that adaptive mesh refinement really only worked for compressible flows and sort of embedded 2D surfaces within 3D. Okay. Now our meshes are 1,000 times finer, which means that I can resolve the near wall region, and adaptive mesh refinement is starting to do the right thing. There is a series of problems that are fixed, that are fixable, and that are open. The fixed problems are, how do you pick out the regions of refinement? There are also, how do you actually refine the mesh? Meaning, how you make small cells out of big cells, and how do you agglomerate small cells into big cells in course? This is all fixed. The fixable problems are making sure that mass conservation, momentum, and energy conservation in the mapping between coarse and fine meshes is fine. I think this is fixed or fixable because it should work and we understand what's going on. The final one is doing that on a high performance computing. On tens or hundreds of cores, I really have no problems. On thousands of cores, doing adaptive mesh refinement without doing dynamic load balancing makes no sense. Dynamic load balancing has been implemented. It has been implemented a number of times, and it's not great because dynamic load balancing on its own doesn't scale. Okay. So now the question is, how much pain do I take with dynamic load balancing to get the benefit of adaptive mesh refinement? So I think this problem will be with us for quite a while.
Okay, thank you very much. So let's look at the last question. Okay, it is from Jason Liang. So thank you for all your contributions in OpenFOAM. I have been using OpenFOAM in all the various versions, Extend, ESI, Foundation for about 10 years. I have used what I think you should in your last few slides, reacting parcel form, I think. So this leads me to a specific question. I have tried to use this solver with AMI, with layer addition and removal dynamic meshing, but it seems there is a limitation in parallelizing the domain across the AMI related cells. So is there a solution to this problem of parallelization across AMI cells with Lagrangian particles? Okay, this is the question.
You see, this kind of question puts me into tears, okay? Because I have to apologize for this not working, because this is shabby coding, okay? So the people who are implementing various types of interfaces and maintaining the versions should realize that all of these problems need to be solved. In reality, what happens is you get a finite amount of funding to do a finite job. You do the job for the client, and then you give up. Okay, so the problem is fixable. There are no fundamental reasons why it hasn't been done. It's just that the project is not completed. Okay, so on the positive note, I can tell you, you have access to the source code. When the particle hits the AMI, you have the addressing, you can move it on to the other side and carry on tracking it. And in reality, this is quite a job, and I need it done in one of the baseline release parts so that we can carry on doing the right thing. That's the life of open source software. And if it makes you better, Fluent and Star CCM Plus are full of problems like that as well. And the software develops at all times.
Okay, thank you very much. So we still have some questions, but because of time limitation, we have to stop here. Okay, so if you would like to still, discuss with Professor Jasak, maybe send an email to him. Okay. Yeah.
Also, Hrvoje, you could just collect the questions so that they are not lost and email them to me.
Yeah.
And I'll email them back to you, because if we put the recording online, we have a possibility of adding some more questions.
Yes.
Please allow me to thank you for this invitation and for this experience. Having more than 200 people online is quite exceptional, and I'm grateful for your effort in organizing this.
Okay, thank you very much. Thank you, Professor Jasak. This is actually a very precious opportunity, for us to learn directly from the OpenFOAM director. I myself actually used the OpenFOAM for about 10 years, starting from Cambridge. Yeah.
Right. Fantastic.
At that time, actually, my PhD supervisor, Nandas, asked me to learn it. So I use it till now. Yeah. Okay. Thank you very much.
Okay. Yeah. Thank you. Bye-bye, everybody.
Yeah. Bye-bye. Thank you. Thank you for your support. Bye-bye.
Thank you so much.
Thank you. Bye-bye.
Thank you.